when you mix red light and green light, it looks yellow to us, and it looks the exact same as if instead of mixing red and green wavelengths of light together, that you just had a yellow wavelength of light. And the same happens with green light and blue light. If you mix it, just looks like the same as the wavelength of cyan light would look to us. And that's actually a very good reason for that, because with the way our eyes perceive light, if you mix two colors, if they're close enough, like red and green for example, because the color that's like halfway between or in the middle of red and green is yellow, since both, if you mix an equal amount of both, then the average is just yellow, and since they're mixed together, that's what we see. It looks the same to us as just the wavelength of light that's yellow. But so mixing and going from red to green shows an accurate representation, and so does from green to blue, of the visible light part of the electromagnetic spectrum. And on the color wheel, it's just like that as well. It starts at red and then fades into green and then into blue, and that's all fine. But then after blue on the color wheel, it starts going back to red, and on the color wheel it does that just to loop back around, so it's a continuous wheel. So it goes from red to green to blue and then back to red. But then this has also led to quite a misconception involving the electromagnetic spectrum, because the electromagnetic spectrum goes in increasing frequency. It starts at red, then gets yellow, green, cyan, blue, increasing frequency. But for some reason, people think that it then keeps going past blue into purple and stuff, even though that's only on the color wheel, because if you kept going like that past blue, if you kept going into purple, and if you kept going along the same trend, you would just get pink, and then you'd just go back to red actually. And so then it's just like the color wheel, then you're just looping back. But that's not how the electromagnetic spectrum works, because this whole section of the color wheel, with the ranging from blue to red, where it cycles back on itself, are mixtures of red and blue, let's say. But it's very important to note that the electromagnetic spectrum does not continue like this, and it can be easy to see that because the electromagnetic spectrum increases in frequency from red to green to blue, and then past blue must be the next even greater frequency, which for some reason people say is violet, as in the purplish kind of colour, even though that's just a mixture of blue and red. And even though it is a mixture of blue and red, and a mixture of red and green, for example, is yellow as a mixture, but yellow is also its own colour, and the thing about these colours is, like the mixtures of red and blue, is that they're not actually, no wavelength of light can give you those colours as well as the mixture. You can only see it by mixing red and blue light, yeah? But let's say there was a wavelength that did make pink or purple light or whatever. Let's say there was a single wavelength of light. It would not be a higher frequency than blue, because it has to look the same as that mixture of red and blue. So it must be in the middle or the average of it. Remember how yellow light is from red and green light, but the actual, even the frequency itself is still between red and green light? This works the same here. It would be between red and blue on the electromagnetic spectrum, because otherwise, why would a combination of red and blue light look the exact same as this? Even if there was a wavelength or frequency that was between red and blue, it would not be past blue, because it would be between blue and red. So if anything, it would be a lower frequency, not higher. But it doesn't exist anyway, so yeah, I'm just saying that the logic just doesn't make sense if you go past blue and then into violet. It does feel like kind of a new sort of wavelength when you go that way, but really if you keep following that way, you'll just go back to red, and that is only a part of the color wheel, not the electromagnetic spectrum. And it doesn't really make sense to talk about mixing two frequencies on opposite sides of the spectrum. They're just too far apart. But in our eyes, of course, we had to see these colours as something, so we see it as purples and pinks, but they're not their own wavelengths. But then, in a rainbow, why can we see some purple? Maybe there is a wavelength that appears like that, and it's not just a mixture of red and blue. And that colour actually does appear after blue, so why is that happening? Well, sometimes it's that it is just blue, and that you think there's purple, and honestly there's not. But sometimes there actually is purple there, but not because that wavelength or frequency is past blue. That's not the reason why. It's because when rainbows form, there's the main rainbow, which is the brightest and most visible, but then there are also like other rainbows called supernumerary rainbows, which are much fainter and much less intense, but you can still faintly see them, and sometimes the red of one of those fainter rainbows overlaps on top of the blue of the main rainbow, and so that's a mixing of red and blue, so then it appears purple to us, but that's not the actual continuation of what's past blue in the spectrum of light. That's just overlapping.